Hello, everybody. In today's lecture, I will be introducing you to a new concept, uh, which is the matrices. Matrices are the building blocks of linear algebra, and what we will learn in this video will be the properties of matrices, and especially the operations involving matrices. So a matrix is um, a bundle of numbers. So for instance, here's an example of a matrix: 2, 3, -1, 4, 0, 2. So this would be what we would call this matrix has 2 rows and 3 columns. And as a result, we would say that A is a 2 by 3 matrix. All right, so this is what we call as a 2 by 3 matrix because it has 2 rows and 3 columns in it. We can do quite a lot of stuff with matrices. Let me first show you how you guys can add 2 matrices. Say, for instance, we also have matrix, another 2 by 3 matrix. Let's say -3, 0, 1, -1, 1, -1. So we have these 2 matrices A and B, and we would like to add them. The first order of business is to check whether both matrices are the same type. Namely, they have to be the same, they have to have the same dimensions, and indeed B is also a 2 by 3 matrix. So as a result, you can indeed add those 2 matrices. So A plus B, the way we would add it will be the following. We're going to add them component wise. So 2 plus -3 will be -1. 3 plus 0 is a 3. -1 plus 1 is a 0. Then we go to the second row. We add, okay, so actually let me introduce you to a little bit more technical jargon. So when we add these 2 terms, what we say is these terms are both on the second row and first column. So in a sense, they are, we can even represent it in the following way. You will see in some books, well, in most books actually, that this entry is just A21. A21 is a 4, and similarly B21 is a -1. A21 means the entry of matrix A on the second row, first column. And the same thing for B, right? So we want to add those 2 entries when we write a number over here for A plus B. Does that make sense? So therefore, 4 plus -1 is a 3. 0 plus 1 is a... Oops, sorry for that. Oh, I messed up again. All right, so how did I do that? Okay, there we go. 0 plus 1 is a 1. And 2 plus -1 is just a 1 as well. That's it. That's the sum of these 2 matrices. In a similar way, we can calculate their difference pretty much the same way, component wise. So the difference will also be a 2 by 3 matrix, but this time we will subtract the entries component wise. So 2 minus -3, so that's just 2 plus 3, which is just a 5. 3 minus 0 is just a 3. -1 minus 1 is -2. 4 minus -1 is a 5. 0 minus 1 is a -1. And finally, 2 minus -1 is a 3. That's it. That's the difference of these 2 matrices. Now, can we multiply those matrices? A times B. Is it possible? The answer is no, you can't do that. It turns out that for multiplication, we need to have the dimensions satisfy another property, and let me just go ahead and show that. For that, let me just recopy the matrix A, which is 2, 3, -1, 4, 0, 2, 2, 3, -1, 4, 0, 2. I'm going to introduce another matrix, say C for instance. C is 1, -1, 2, 1. So I claim that you can multiply these 2 matrices. Notice that A is 2 by 3, C is 2 by 2. Actually, you cannot multiply these 2 matrices, my bad. Well, we can multiply in one direction. The only way you can multiply 2 matrices, A and B, is if the dimensions of A and B are m and n, m rows and n columns, then you can only multiply this matrix with another matrix if the dimensions is n times, say, k. Do you guys see how the middle dimensions match? That's only when you can multiply them, and the resulting matrix AB, for instance, the resulting matrix will have dimensions m by k. Okay, so that's the idea. It turns out, based on this description, it's clear that matrix multiplication is not commutative, meaning A times B is not equal to B times A. That's one observation we can immediately do. A times B, is not equal to B times A. So as a result, when I look at these two matrices, I cannot multiply A times C. Why? No. This one is a no. Why? Because A is a 2 by 3, C is a 2 by 2, and their middle, the last entry, the second entry in the first matrix and the first dimension of the second matrix, they don't match. However, C times A is possible. Why? Because C is a 2 by 2, A is a 2 by 3. Aha! So this is the 2's match. So therefore, the resultant matrix will end up being a 2 by 3 matrix. So it will be a 2 by 3 matrix. What it means is, and let me just try to fit it in here, it will have 2 rows and 3 columns. While at it, we can I can also show you guys how this calculation is done. Let me change my color here. Okay, there you go. So the way the multiplication works is the following. So C is the first matrix, A is the, actually let me just write it on a new space because it will be confusing here. So we want to multiply 1 minus 1 to 1, that's C, with 2 3 minus 1 and 4 0 2. So this is C times A. There you go. All right, so the way we will do is the following. It's actually a very simple idea. We will make a component-wise multiplication of the rows of matrix C with the columns of matrix A. And that will give us the desired input. So for instance, because we want to calculate those 6 numbers, we already established the answer should be a 2 by 3 matrix. So the first entry of that new matrix, resultant matrix, will be the product of the first row of the first matrix and the first column of the second matrix, but component wise. So meaning 1 times 2, that's a 2, minus 1 times 4, that's a minus 4, 2 minus 4, 2 plus minus 4 is minus 2. So that will be, this entry would be minus 2 here. How about this entry? So, well, this entry is the first row, second column. So, in the resulting matrix. So, I need to multiply the first row here with the second column here. So, 1 times 3 is 3. Minus 1 times 0 is 0. 3 plus 0 is just 3. You guys see that? Let's go ahead to the next entry, the first row, third entry, third column entry. All right, so it will be still the first row from columns from matrix C multiplied with the third column of matrix A. Let's do it. 1 times minus 1 is minus 1. Minus 1 times 2 is minus 2. Minus 1 plus minus 2 is minus 3. And it's very, very easy. We can do the same thing here. So for this entry, it's the second row, first column. So we need to, this time, we need to multiply the first row of matrix, the second row, I should say, of matrix C, the first matrix, with the first column of matrix A. 2 times 2 is 4. 1 times 4 is 4. 4 plus 4 is 8. You guys see that? So let's do it again. 2 times 3 is 6. 1 times 0 is 0. So that's a 6. 2 times minus 1 is minus 2. 1 times 2 is 2, minus 2 plus 2 is 0. There you go. So that's the resultant matrix C times A. And like we said earlier, A times C, there is no such thing, right? A times C does not exist. Does not exist. However, C times A is what it is. Matrices has some very, very interesting properties. Let me list a few of them. One of them is the inverse of a matrix, which we will go over in the next video basically. But the idea is the following: when there exists a unique matrix which is the inverse of any given square matrix. A square matrix is an n by n matrix, n rows and n column, an equal number of rows and columns. And if that matrix A is invertible, it's when you multiply with its inverse, it will give you a diagonal entries. Diagonal entries all ones, and all the off diagonal entries will be bunch of zeros. Interestingly, if you were to left multiply our matrix by that inverse, that would have given you the same result as well. I said interestingly because remember earlier we mentioned that matrix multiplication is not commutative. For instance, when you multiply the numbers 3 and 5, that's 15, and that's also equal to 5 times 3. That thing is not gonna be satisfied, not necessarily true for matrices. A times B and B times A are not necessarily equal to each other, not necessarily. All right, sometimes they are. Under some special conditions, when the matrix A is a normal matrix, it is. But otherwise, most of the time, it won't be. So that would be a better way to think about the problem. And in the next video, we will also have a look at, we will learn how to calculate the inverse of a matrix, but also we will learn how to solve an equation involving matrices, basically. So that will be pretty cool. So just to finish, wrap up this video, I would like to also finally talk about the determinant of a square matrix. So suppose that you want to find the determinant of this following matrix, 2, 1, minus 1, minus 1, 3, for instance. The determinant of this matrix is, the 2 by 2 case is easy. Let me just go over the 2 by 2 case first. We will just multiply the main diagonal entries, which is 2 times 3, 2 times 3 minus, and then the other diagonal, minus 1 times 1. That's it. So 2 times 3 times minus 1 times 1, and that is just 6 plus 1, which is 7. All right, so the case of a 3 by 3 matrix is a little bit more annoying. Suppose that we want to calculate the determinant of, say, this following matrix, 1, 1, 1, 2, minus 1, 3, 2, 0, 1. Okay, so suppose that you want to calculate the determinant of this matrix. So how would you do that? There's a couple of different ways of doing it, but ultimately you guys can imagine in upcoming videos we will learn how to do it using Excel. Excel does it very efficiently, but the way we do it is the following. All right, so the way I learned it when I was in, I believe I learned this concept in high school. So what we will do is we will put some imaginary plus, minus, and plus signs. And here we go. So this one is a plus 1. We will multiply it with the determinant, which we usually put the determinant inside absolute values of all the other entries except the entries in its own row and column. All right, so 1 is part of this row and this column, so we want to make all the other entries, use all the other entries in the matrix, minus 1, 3, 0, 1. Do you guys see that? Next one will be minus 2 times, because we did an imaginary minus sign, a 2 here. And now I will just visualize, I will just remove the first row and the second column from the picture. What will be left will be 1, 1 and 0, 1. Do you guys see that? And finally, the last entry, plus 2, and then the matrix involving that one will be 1, 1, minus 1, 3. That's it. And well, the good news is we already learned an efficient way to calculate these individual matrices, the determinants in the case of 2 by 2. So let's quickly do it. So we have a plus 1 times, the determinant of the first one is minus 1 times 1 is minus 1. The other diagonal is a 0. So that one is really a minus 1. Minus 2 times, so the second one is 1 times 1, 1. Minus 0 times 1 is 0. So this is also a 1. And plus 2 times, 3 times 1 is a 3, minus 1 times 1 is a minus 1. So 3 minus minus 1 is 4. And finally, this thing comes out as minus 1 minus 2 plus 8, which is just a 5. So the determinant of this 3 by 3 matrix turned out to be just equal to 5. It turns out that the determinants of matrices are crucial in making a lot of different linear algebra calculations, and I wanted to provide you with that as well. Awesome. So let me stop the recording here. So in the next video, we will directly start by using uh, both matrices and determinants to actually solve systems of equations, linear equations. Hope to see you guys then.